the ensemble.
So far, we have made some headway with this particular symmetry by using just things that are quite invariant, like the characters. You use the characters to get correlation tables, and the list of the characters are right here. And there are a couple of interesting functions that we talked about for the group D3. Remember, there was the maximum, the order of the group, first of all, that was 6 for the D3. It's 24 now, so we've grown a bit here. And then the rank, that's kind of interesting. The sum of the dimensions of the irreducible representations is the number of, the maximum number of commuting observables, if you want to use physical terminology. In that case, it comes out to 10. So we have possibility to see that number 10 today come up. And finally, just summing the dimensions to the 0th power gives you the number of classes and the number of representations. Your group have twice the rank of its order. Don't see that very often. Okay, so today we're going to go outside of the realm of the things that are invariant. The first step outside of that is to split the all-commuting idempotents that each belong to our irreducible representations. So once you've done that, that's something that makes things that are not invariant, not something that you would usually publish as numbers that could be printed on stone or gold or some precious metal. These numbers that you make are whatever works, whatever the physics demands. So when we decide to pick something to split one of these all-commuting idempotents that is by itself invariant, and all-commuting means commutes with everything in the group, once we decide to do that, that's a choice made hopefully for physical reasons to help some sort of thing. So we're going to be picking on a projector from this group, the C4, to break the idempotent. And all of the physics that we get today will pretty much be just that operation. But that operation isn't trivial. The C4 has 4 elements, so the projector will consist of a sum of 4 of those elements. And then the all-commuting projector for this thing is sum of 24 elements. We got to multiply those all together, right, to make the idempotents that are irreducible. And as I say, not unique. The choice that I make there is very crucial. So that's the sort of the message of today, and then we'll be able to do a bit with that. That will let us actually calculate some eigenfunctions and eigenvalues for, we'll take an octahedral case, we'll take the simplest tunneling case, and we'll take it as an analog to the simplest vibration of the molecule SF6, an octahedral molecule that can only vibrate radially. So you'll see how all this fits together, but that's the order of the day there. It has some unpleasantness, though, and that splitting of the idempotents is not a trivial operation. So just recall the very basic structure of this group, and the one, of course, that we're most interested in for future work is the icosahedral symmetry. So it's a giant compared to this. So the jump from D3 to O, which we're making today, is probably a lot smaller than the jump from octahedral O to this fellow. And more about that later. Watch this space. Now remember that the group O is just half, that half right there, O symmetry, of the OH group, which has, in addition, to the rotations that are here, say here it's 180 degrees, and here's a minus 90 degree, that's a plus 90 degree, all around the z-axis, okay? And that is added to with a reflection, the number 3 reflection, the reflection in an x-plane, and then the number 4 reflection. And each of these reflections, these ones that are numbered here, are reflection planes such as the sigma 1 that goes right through here that's perpendicular to the 180 degree rotation I1. And sigma 4 is a reflection that is perpendicular to I4, which I will maybe be able to find here easily. There's 3 right there, there's 6 right there. Just these little tiny letters, which are quite small. But you can see on the actual big model there and on the miniature ones that are lying around here that those are more clearly marked. You can see the...
There's I4.
There you go. And all of the operations are in smaller characters, and then the state positions are in the large numbers here. So let's see if I can find I4. I4 obviously must be, anybody spot I4 here? Here's 3, 5, 1,
I
6.
think that it might be a 4 up top.
Yeah,
Oh, there it
on
is.
the corner.
It's by your knuckle, your
On the corner.
pinky knuckle.
There it is, thank
Yeah.
you. Right there. So perpendicular to that axis, which is going right through there, it's sort of hiding in the corner there, perpendicular to that axis is a plane sigma 4. Okay? And you can see what it's doing. Sigma 4 takes whatever was in the unit slot and slides it over to the sigma 4 slot. So it's one of the easiest to find on this particular choice that we've got. And there's the other side, and finally bringing it around here is
No, that I4 is that.
there's the x-axis is pointing at us right now, and I'm able to see minus z-axis. I think we're going to play with that thing a little because we need to use cosets to perform the splitting of the item code. That is what's really, I would say, the hard part of this particular derivations that we're going to be doing here today. Okay, so we're only working with the rotations on this particular one. So I very quickly compare some of the stuff that we did before, now tabulated in a more neatly organized form. In particular, what we'll be talking about today is the correlation between the octahedral group and C4. We'll not necessarily have to use the intermediate step where we look at the correlation between D4 and C4, which is the last thing that we did of this nature in the previous lecture. But and only using the octahedral character table and only these 5 representations to produce some results that we'll do at the end here. But in any case, the D4 characters is something that I've always said, those are things you should derive, just as an exercise. C4 characters right here have 2 imaginary ones. So that's one of the things that we're going to encounter today is a C-type, that's a current carrying moving wave type mode that has complex, in this case i's and minus i's, wave functions and eigensolutions. In any case, this was a splitting diagram that we talked about at the end of there. There are the triplet T representations, 1 and 2, vector and tensor. There's the other half of the second rank tensor. Then this thing actually doesn't show up until you do a cubic tensor, but this one shows up quite early as x squared plus y squared plus z squared invariant. In any case, These two, of course, can't split. There's only one state for each of them. But these and this can split this one in two, and that's the end of the splitting for it. But this one, when it splits in two by going to the D4 symmetry, still could split some more. And we're going to take it all the way to this. So that's the splitting thing. A1 is 004, A2 is 2 sub 4, E is this, two of those together, 04 and 24, and then the T1s and T2s make use of 1 and minus 1. The T1 makes use of the 04, the T2 makes use of the 2 for appropriate, since the angular momentum associated with T, and that's perhaps the reason for its subsgroup, although that's probably a coincidence. Number 2 comes from angular momentum 2, which it belongs to since it's a second rank tensor. Okay, so this is all a review of sort of the physics and mathematics sort of tied together a little bit. If there are any questions, please bring it up, because anything that you can know about the symmetry and the physics that goes with it is to your advantage. Particularly for the kind of work we're doing around here with all these D-type compounds making various phenomena and devices that I mentioned before, the splitting of the angular momentum 2 into two pieces that are a triplet RT2 and a doublet RE. Okay, so this is a more civilized splitting that we'll use in the following lecture, where we'll make full use of all of the irreducible representation matrices. Today we're going to confine ourselves to those which are diagonal projectors. No PXY, it'll be PXX and YY and ZZ typically. Okay. Still, it's going to be enough for us to get surprisingly a lot of physics. Okay, so let's go ahead and mention some that will come later. Here I'm once again putting down the two that are easiest to do and also have the most physics that we can show quickly. But I would mention that if you make a correlation table between groups like D2, where you're using the X, Y, and Z 180-degree rotations as your symmetry, and you consider another D2, which exists in the cubic group that consists of, well, 3 180-degree rotations, but except for this one, these two are diagonals of the cube axes, the I3 and the I4, which we'll be playing with a lot today. This is a group that is unnormal. I've kind of, as respect to the group O. This one is a normal subgroup in the sense that anything in the octahedral group that transforms this subgroup leaves it alone. It just permutes the X's and the Y's and the Z's. But if you transform this one, a lot of, there's quite a few of these groups hiding in the octahedral group. This is just one of them. I do a transformation, I get some of the others. Any pairs of the I transformation, we have 6 of those I transformations. So there's a number of pairs that you can make there. And they have a little bit of a different correlation table than this one. And the correlation table here with this very normal subgroup, this one right here, has an ambiguity. That is, it's not just one representation there. Something more has to be done. Whenever you get a 2 in one of these correlation tables, you have more work to do, some more splitting to do in order to label everything. That's a message that I also want to make very clear. But so far, all of our correlation tables, and this is going to hold for a lot of things we do here, come with just zeros and ones. But this one is different. The idea that when I split this thing, well, I'll discuss this technicality later on. I think that we can wait on this particular item for now. We've got a lot to do here, so let's get started. But I would like to show you the OH side of the story. And this we'll see today sort of in accidentally stumble on this. Compare the correlation table that we'll be using here today that involves C4. Okay, the correlation table octahedral to C4 consists of an A1, an E, and a T1 for the scalar representation. Now this is the scalar representation of a C4V group, which is a subgroup of D4H, and then finally going to OH. So this is the full professional correlation table you need for octahedral perovskite type solids, with all of the parities and reflections getting their chance to voice the symmetry. And what you see here is an A1 that has a G attached to it, an E that has a G attached to it, and then you don't get to use the T1G. You have to go all the way down here almost to the bottom, and T1U shows up. So when we work out the actual pictures of the waves for the cluster 0 mod 4, and let me back up here just to make sure you know what I'm talking about on the screen where it isn't on the chalk tray. Here we're talking about the cluster we'll work with today, 1, E, and T1, but of course that's just the octahedral group. It doesn't know about parity, whereas this one does know about the parity. The parity being odd for this and even for these two. So that's something we'll see come out today when we work out that. As I said, that's an analog between vibrations, radial vibrations of a molecule, and then the quantum mechanics of the tunneling of the rotation in the rotational part of this. So it's two types of spectroscopy, very different types of spectroscopy to see those phenomena. All right, let's see if there's anything else here that I can say. Yes, there is always the groups C2V, this guy right here, as a subgroup of C4V, an isomorphic cousin to D4, both of them of order 8, but this one has some subgroups, C2V and C4 correlation. Now there are once again C2Vs that are normal and there are C2Vs that aren't. The one that's normal gives us an ambiguity, even with the parity. I have two EG states. That's a degeneracy ambiguity that you then have to do some more splitting or do something to rectify. This one has all ones. There's a lot of ones there.
Dr. Harter?
Yes.
D4 is the one that has like four rotation operations, 2 reflections across the edges, and 2 reflections across
You're asking about D4.
Uh-huh.
Yeah.
2 reflections about the edges and 2 reflections.
No reflections for D4. It's all rotations. What you're thinking of the isomorphic guy, C4V.
Cyclic.
The 180-degree rotations that are perpendicular to the main axis have reflection planes normal to them. If you use those instead of the rotations, you get this group. Just as you remember when I showed D3 and C3V, right? It's got reflection planes, 3 of them.
But those are a little bit easier, right?
They're what?
D3 and C3
Easier.
and C3.
D3,
Hey, it's an odd number.
yeah,
Yeah, it's prime.
It's
In
prime?
algebra, when
Yeah.
it gets prime, it's easier.
yeah, right. Yeah, these two are isomorphic, just like these two are. Now, we don't go to 5, but we do have D6, okay? Over here, we have a D6 and a C6V, so those two also
So-
analogous. But this one's made out of outer products, right?
Uh,
These guys are primal.
So if I said, well, that molecule right there has like a D5, right? Symmetry.
You talking about this guy?
Yeah, if I look at it from
Boron
the top,
hydride?
yeah, if I look at it from the top, I think it has like a.
Well, if you look at
fivefold
any of the axes,
Uh-huh. It has
okay,
it's-
you're seeing a hexagonal. Yeah, and that happens a lot when you look down. But actually, no, I think
See-
I misspoke. You
It's
see
a
a
thick
pentagonal.
Yeah, that's.
Yeah,
Look
right.
down
Pentagon.
a
Yeah.
triangle.
So it has like
I was thinking of buckyball. You have a phony hexagon there.
Yeah, and you have 5
Right.
too. Like
It's
the-
really
the
only
smaller
threefold.
one.
This bond is slightly longer than this bond right here. This one's on a pentagonal, this one's on the pseudo-hexagon. So this
Pseudo-hexagon.
this bond is a little tighter.
It's close. To the
Yeah.
eye, it looks like a hexagon.
Yeah. Well, we made it so that it was a perfect thing. By making these all the same length, it becomes a hexagon. And that's one possibility. See, one of the ways to think about this solid is you take a dodecahedron and saw the corners down. You just sand the corners down. Okay, if I keep this going here, then I'll make the threefold axis be an intersection point on a big pentagon, and there'll be another big pentagon right there. That's dodecahedron. 5 times 12 is 60. Okay. If I sand the other thing, if I sand this one down, then I end up with, let's see if I'm thinking of this correctly here. That's what I did to make this thing. I sanded this one down so I get that. But then if I bring that together, bring all those together, then I get to icosahedron with 20 triangles. Okay, so the hexagon finishes itself with a triangle, an equilateral triangle.
Page 2, we have some links to illustrations
Yeah.
and papers.
Yeah, there's a lot.
Dissertation papers and
There's a whole-
such.
About that molecule?
Whole Bucky section.
Yeah, I think I would like to read about it.
Yeah.
Please do.
We'll get, yeah, it's a monster, I'll tell you that right now. A beautiful monster. Okay, let's go ahead and get to the stuff that's kind of the hard work here, and that is splitting idempotence. And the basic idea here is we look at our character tables and our correlation tables to see what's going to split, and we're in particular interested in the correlation between our O group without any reflections, all rotations, and then this thing is all rotations, a subset of these, okay? And when we do that, then we get this correlation table that we developed before. So, using that correlation table, I can set up the algebra for the splitting. That is, I'm going to be taking each of the idempotents associated with A1 and A2, there they are, and of course that's a one-dimensional one. I can see they cannot split, so I'll just be writing an irreducible idempotent notation in place of this one, because this one is irreducible right now. The scalar is just the sum of all the group operators in the whole tetrahedral group. And this is a sum of all of them also. The only difference is that for it, the other half of the octahedral group, and that is 6 operations plus another 6, that's 12. That's half of the group. Doesn't look like half because these guys hog more of the character table by having the dimension there. But that splitting there, everything on the right half has a minus sign. So this is the sum of all the group elements. This is the sum of all of the first half minus the second half. That's the pseudo-scalar of the octahedral group. Okay? Well, right away in the next row here is the rank 2 tensor, the two-dimensional one, if you recall, that we worked with very early on to get our irreducible representation, at least a particular kind of irreducible representation. happen to be pretty close to the one we're going to use today. And then the triple, these guys, they're splitting in three, this guy in two, and that's what we have to do today, is split these guys up so we can use them to make eigenstates. And here's the table that I would put up to how to do this. Basically, I just say, okay, this guy I'm not going to do anything with because he's already as irreducible as he's going to get. Same with this one. But this one I'm going to label by 2, 4. That is, there's the double index notation for the irreducible projectors of this particular type. But these are invariant. Every time I do this with some other subgroup, I'm just going to put a different label down here. It will be for the same operator. There's nothing funny going on. This is kind of the abelian part of this class structure. It's here that I can get different things, but this time I'm going to get these two different things. By taking the irreducible projectors of C4 and multiplying by this one will give me this. When I take the product of this with that big guy, I'm going to get this thing right here. Okay, and the big guy I'm talking about is this thing right here. So PE times that gives me that. And then big PE times this little p sub 2 gives me E sub 2 twice. And remember, we have a global and a local index, is the way we think about the left and right indices of our projectors. And then the same thing is true as I go to split PT1. I've got to multiply it by this. That's going to give me a fourfold scalar type projector as my first irreducible idempotent projector. Then it's going to give me 1 and minus 1 in the lower indices. This one coming from this one. 3 mod 4 is minus 1 mod 4 for this cyclic group C4. So is that clear? That once you've got this thing, this is invariant. This is too, except the individual projection operators there, they're up for grabs. Okay, there's a lot of different ways to split these things, but they always has to come out to the splitting of 3. Okay, that's the invariance that's being stated by the character table putting a 3 here for the dimension of the irreducible representation. In that case, of the unit operator. Okay, is that clear? That's, the thing. So we're just now stepping the boundary past the first stage of group analysis for physics into the second stage, which is to split these idempotents.
Could you pause there just for a sec?
Yes.
It's interesting, you mentioned that there were 10 observables for this problem.
That's right.
And you just tabulated all possible in which they agree upon the symmetry choice. Both the internal and the external are in agreement.
Good point. There is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of these things. Okay? So that is the rank. And all of these things here, each of these projection operators commute with all of the others, but not with all of the elements in the group. Okay? That's important. These guys do commute with all of the elements in the group, but as soon as you split them, individually they don't commute. But whatever commuting this thing doesn't do, this one or this one makes up for it, you see. So that this ends up being all commuting. These are all commuting operators. They commute with everything. These do not. So what we're asking for in that rank is the maximum number of commuting observables, because that's one way to state it. There they all are. And that's kind of a proof of that theorem, that the sum of the dimensions is the rank. Once you agree that those things do what I said they did, right? So they're, in a sense, a complete set. And that's the name of the game for this particular group, is we're going to be studying all sorts of different ways that its symmetry dictates, but in each of those cases, if you do it right, you're going to have 10 observables, and only 10 that can be mutually diagonalized, because they can mutuate, but not with all the other guys, or practically any of the other guys. Okay? It's an exclusive club, but it's not the only one, right? There's an infinite number of different choices depending on what subgroup correlation you take. And right now we're favoring a subgroup that has circulation. We're doing C-type stuff with C4. It's going to have imaginary numbers in it.
So
See
for
them?
example,
Right here and here.
so if I would like to analyze the molecule NH4,
N, and then 4H's, probably tetrahedral. Okay, that's probably a tetrahedral.
Yeah,
If you can make it, I'm
yes.
not so absolutely sure about NH4.
Oh,
Because
sorry,
NH3 is pretty stable, although it's not really happy, right? Because it does the inversion.
So-
Okay, it's a quantum molecule.
yeah. So I'm trying to see like if I can apply this symmetry analysis to like a molecule that has like a 5. Oh, you know, I think
I had
benzene.
benzene is a hexagon, very stable.
Oh yeah,
It's a
benzene is
planar
hexagonal.
hexagonal.
One of
Those
these
are
Truly
fine.
one of these
hexagonal,
sugars,
not
though,
sort of a fake
one of-
guy like
Those
this.
resonating bonds
One
are
of these
wonderful.
sugars is a pentagon, though. Well, I
Pentane.
Well,
pentane. So can I use like
Much less stable than benzene, yeah.
Can I use this symmetry analysis to analyze pentane?
You bet, and that's one of the other
It-
problems
but
besides
precisely-
D4.
It would be a different group.
Yeah,
What shape does it have?
yeah.
It's a
You look in the
5-fold
lab?
symmetry.
So it's going to be either a D5, or depending on how those end
If
bonds.
it's bent, it would be C5,
For the
B,
H's.
perhaps.
But
yeah.
you know it's got C5 in it
No.
as a subgroup.
And that was our first warm-up exercise for buckyball, was to do a D5. Because
Ah.
that's the subgroup many times in this thing.
Yeah, I can see that.
Yeah,
David
many
Weeks.
times.
His
Yeah.
paper's on page 2. David
Yeah.
Weeks.
Yeah.
Okay. I
And-
mean, it's
and
because
about-
I'm trying to see whether I
Kind of
can
correlation.
relate those like observables to like a molecule and use like the symmetry of the molecule,
Yeah.
and like when you say like the rank,
Mhm.
I say like, well, I can use the set of commuting observables to define like each of what I do measure in the molecule, and I can use that to do that. And then I thought about like
This
like
little
the
trick
pentane.
here.
I thought about like the painting,
Yeah.
about like how you can like use like the,
Mhm.
like gymnastics to start doing Pokeball.
And it will do all the things that
Nice.
these guys we're talking about do. It has vibrational modes, and then it
Yeah,
has
because
the...
you have this.
Yeah, that's
And
right.
then
You have all kinds of
these-
vibrational
these
modes.
planes.
Some of them very slow, some of them much tighter, higher frequency. But you also have, once you've done that, you have the rotational behavior. Okay, which is, a lower frequency by far, but still on top of the vibrations. Okay, so we got to split these three. And these three come just from the numbers in the character table here. 2, minus 1, 2, 2, minus 1, 2, 0 and 0, and then divided by the dimension over the order of the group, right? That's the numbers that we're looking at here that have the 8 and the character on top. Okay, so that's what we have to do. We have to multiply each of those guys by, well, we're just going to work with this one today, but we're going to go ahead and finish the job for the others. Okay, this one's obviously the easiest one to do, particularly when it comes time to do that. Well, we already knew the answer to that one. It's going to be getting the answer to this one, and this one. Okay, now, the question, we're using two kinds of notation here. If you go back to the old book, Principles of Symmetry Dynamics, these are the notations for the various operations of 120 degree minus 120, roughly speaking, 180 XYZ, 90 XYZ, minus 90 XYZ, that's all in a class together, and then 180 around the various edges. We were looking for I5, or I was having trouble finding I4, I guess, this morning. I wasn't feeling euphoria when I was not able to find phoria. But anyway, that's here or there. But you see, we use the same notation for the i's, but these are different because we have these little tildes here to indicate a cubic, which is the -1 modulo 4. And we use Greek letter rho for something that was squared. And the same thing with the r's. We don't put squares, we put little tildes for them. Okay, is that? I just want to make sure. And we're going to jump between these two since we'll use both figures, kinds of figures from both of the books. Okay, how's this do? Now, remember, this guy is an all-commuting. This guy is an all-commuting guy. So you can put this projector from the C4 group on either side. Not going to change the results. And the examples that we'll be spending most time on are those triplets right there. Okay, now when we do this multiplication, that is, we take the C4 group that consists of, and remember what these symbols stand for. First of all, there's rho Z. Okay, that's this guy right here. So that's a 180-degree rotation that I take as a second in the thing, not the 90-degree rotation. It makes sense to put them the other way, but it's kind of nice to keep the complex numbers together. So I'm taking the 90-degree and the -90-degree as 3 and 4 in positions of the C4 subgroup. And then we're going to start multiplying by each of the other elements in the group until we've exhausted the entire group. Okay? So the next thing, I've already used rho Z. Let's try rho X. And rho X gives you 4 new elements, including rho Y, as a first coset of the subgroup. Okay? So there are the 4 elements. We now have 8 elements accounted for. We've got a ways to go yet. I got to find another element in the group that's not in this set of 8, and I pick R1 just out of a hat, and I get these 4 guys here. I end up seeing R4, I1, and RY. So R1 times C4 gives you this coset right here. And these are called left cosets because I'm hitting it, multiplying it from the left, which is most common in mathematics to do that. You come in from the left in all most mathematical things we do. But in any case, then I go and pick an element that's not there, like R2, and I get sort of a similar looking thing, except this one is the inverse of the 90-degree rotation, and I2 is very different from I1, as is 3 is different from 4, and so forth. So we're more than halfway through the group at this point. We've got 2 more cosets to go, and there they are. This one, kind of the inverse of the 1 and 3 120-degree rotations, and then a 90-degree rotation around X, and an I6 sort of pops up there. And then finally, this is the last coset that has the R2 and R4 inverse, minus just like these are inverse. You got little tildes on top of it. Okay, so what do you do with those cosets and how do you handle them? Because that's what's going to come up when you start multiplying each of the elements in this item mode projector with these sums here. Okay, and the sums have numbers on them, so it's important to keep track of what order they're in and all of that kind of stuff. So, what I want to make clear here is when you have these cosets, and where are the cosets on our little slide rule? Okay, well, we start out with a subgroup here, 1 rho Z, RZ, and RZ tilde. That's 0 degrees, 90 degrees, 180 degrees, and then minus 90 or 270 degrees. Remember, only rotations on this cube here, but of course the one sitting on the desk there has twice as many things. In any case, the idea is that this whole face here gets moved to another face by another element that's not in this collection. So the next one, if I do a row X, that is if I find the X-axis here, that's this axis right here, okay, and turn that thing by 180, I'm going to dump this thing over here, right? And Al, you're pretty good at rotating that thing, so maybe set it up so the Z is pointing at us like it is more or less here, and that would mean just turning it at the top there you go, okay, and then the X-axis should be facing you, and if you go ahead and do that operations, you'll get something like this. Let's see what you get if you turn that thing over by rotating it around the axis that's pointing at you. That's the X-axis, isn't that? Plus X, okay? Just go ahead and do a 180-degree rotation. Either way, it doesn't matter. That's 90, and there we go, okay? And you see the I4 is not, I mean, it's at the bottom here, okay? But from where we're looking, it's at the top, okay? You see the I4? This one hasn't been rotated, right? So the message is that when you do another operation to any of these cosets, like if I pick any of the elements inside there to do the operation of these things, I'll get the same set of elements, but they won't be in the right order. They won't be in the original order. So I think it's important to see that spelled out, because that's what we're going to have to deal with as we multiply these things. So here is a table, and maybe I should just put it here to show it, but basically, there it is right there. So these are all also the left cosets that we would be getting, okay? They'd be the same elements, but in different orders. So the row X here, for example, times the subgroup in the order that we started with, gives that set right there, exactly. But then if I shift these things over to the way I've done here, I've shifted them, these two, I've switched these two, okay? Well, I'm going to get the result that's up here, but I had to switch these guys in order to get the same result. Otherwise, I would have gotten the things the way you see there. They've been moved from what you see before you rotate there. So this is a way just to see that I can get this thing in 4 different positions, but it'll be the same coset. It'll be the same thing. Okay, there's 1, 2, 3, 4 different positions that those can occupy on that face, depending on which of many operations you do to accomplish this particular coset. Okay, so it's like a set. I don't care about the order in that sense, but I do care about the order as I'm doing this summing, because I'm going to have different phases on each of these group elements. And that's what makes it a hard problem. Okay? That's what makes it a very big arithmetic problem. It's not as simple as D3 projectors getting split. Okay, that was easy. This is more professional. So, yesterday I figured I'd make a big array that would make that easy to tabulate. So I simply put all of these elements in. They're showing the cosets that were responsible for a particular arrangement. So the idea is that this times this is that. Well, that's just rho z squared. We knew that. And then here, a rho z times 1 is that. So this is just the group table written in a funny kind of way, so it's set up to do the product of the idempotents with any sort of numbers I want to put on them. And I do want to put a 1i minus 1i minus I for the 1 mod 4 representation of C4. Okay, so that's and that's as far as I got with this, because this is when the mask type crashed. This thing crashes math type. Okay, I'll be on the phone this afternoon again, trying to get that fixed. But if it's going to crash with octahedron, it's certainly going to crash for the icosahedron. No question about that. So we've got some work to do out there in San Diego, California. And it's just because Apple changed the system 10.13.3. Nothing seems to work properly.
Upgraded.
You mean the computer couldn't run the computation like an octahedron? Like did it just crash?
Well, it crashed for this specific one. It didn't really crash. It just, what it did was it let you edit, and then when you said, okay, I'm done, you looked and it hadn't changed.
Okay.
Wouldn't save your
Yeah.
changes.
So I went back and forth a couple times. Then it crashed, literally. I mean, the application
Spot.
froze. Okay. Now, math type has really been good until this. And the other thing that happened with the new system was you can't control color fully. No full color control of the type. And you know how that's going to hurt me, right? We do everything in Technicolor. Now it's going to be back to black and white for a while. So I was going to color these things to help, but it didn't happen. Anyway, this is the old way of doing it. I've got blanks here that I'm going to fill and try to explain to you what it is I'm doing. What I'm going to be doing here is I'm going to be moving the wave functions around to the right places in order to get the product right. Because you see, the thing that we have to do is we have to take this irreducible item code with equal indices, so that's a saving grace, but we have to do the dimension over the order of the group. That's going to be 3 over 24 for the biggest representations that have 3 dimensions in them. And then we're going to be taking the numbers that we will get. That's what we're after. We're actually after to get these numbers by multiplying what we already know, and those are the representation first of the C4 group, depending on which M you want to pick, and then the character right here of the particular, say, T1 or T2 or E. Those are the 3 that we have to do, the last 3 that actually split. So that's what this is all about. It's just setting it up to do a sum, starting with the unit, which is really easy, okay? The character unit is just the dimension, so there'll be a dimension squared over, and then 4 times 24, 96, the 1/4 coming, of course, from these projectors all have 1/4 as their coefficient of the group elements. So that's particularly nice. We don't have a lot of different numbers here, but we do have different numbers there, so that's going to make trouble for us. Okay, so here is the first row. It's this thing plus this thing. We've got 2 down, 24 to go, roughly speaking. It's not quite that bad, but each of these products here has to be worked out, and that means that we have to be careful where the numbers, namely the 1i minus 1 minus I, in particular, if we're doing that guy. This one, we won't have to do this one because this is a complex conjugate of that one. And then this one right here has 1 minus 1, 1 minus 1. We have to be careful where the minuses go. This one's the easiest one. Obviously, if we do that one, we don't have quite the problem of worrying about the reordering that occurs in the cosets. But that's what is at stake here, okay? So the third one here is now I'm working with a character associated with the rotation RZ. So I'm taking this one class at a time here. I'm going with the one class, and I took the row class. Now I'm taking the R class. Eventually we take the little r class and the I class. And then we'll finish the list of products that we have to do. Here's the RZ inverse element. Here's a row X now. There's the row Z. And you see, that's the problem, is we have to do more than just the one from each class. We have to do all 24. So this gets pretty complicated, as you can see. Now what I'm doing in each of these sets here is I'm taking whatever happened here and doing a switcheroo of the numbers in the order that the cosets really should be. So this is a formula yet to have the numbers 1i minus 1 minus i or whatever put in, and we're not done yet by any means, etc., is what's written here. So you see, this particular way of doing it, sort of brute force, is a lot more paper wasting than just writing numbers down here. And that's the way I say is the best organization that I can think of right now if we're going to do splitting this way. This is the way to derive that. So this is where actually it crashed. And I was just starting to put in the character designations and all of that, and then actually put the space here with a number that we would then add up for each column to get our irreducible projector that we need for a particular representation. So this is the old thing where they're all written out now in sort of the old notation, and the idea here is that we're going to fill in these blanks down here by adding up those numbers. So there's the cosets in the order we started with. There, cosets have all been taken account of, but in a more clumsy way than would be to just write them down in that little array there. So we already got this guy. That's just worth looking at, but it's PE. Okay, so we're looking at 0 mod 4 component of PE. So I've got all 0 mod 4 written there on the C4 side of it, and then I've got the characters associated with the E just from the character table. You see, that's the easy part, is that I only need to use these numbers right here. I don't have to go through and know the irreducible representation of E. I only have to know its characters to do this splitting exercise here. So those have to be stuffed in, and there they are. They're pretty easy. All 2's here, if I'm talking about the 1 or the row Z characters, those are the 2 that have 2 there. Then there's a 0 for a half of the group. So we've got a good deal of zeros popping up here, so that makes it a little easy anyway. And now we're talking about 2 over 96, that's 1/48 for everything. And it just amounts to adding up the columns here with the correct coefficients, okay? So here's what we end up with: a bunch of 4's, and then a couple of 4's in a group of 4, and then 4 minus 2's, and that is the actual projector, irreducible projector for E0404. Okay. Now, if you do a coset factored sum, it's much simpler. It's just 6 terms, and that's in fact what this would. I mean, there's a way to see that that lets you make the calculation on that chart over there more helpful. Now, this is the interesting one. This one is if I just spill all the elements out in the order I'm used to having them and look at the coefficients, and wherever the coefficients are equal, usually within a class, that's a subclass. So R1, R2, R3, and R4 are not in separate classes with respect to this particular splitting, but R1 and R2 are, and there are ways to see that. So it's true of R3 inverse and R4 inverse. These guys stay, that class does not split, but this one does. The 90-degree class splits in 2. And then this splits into 1 and 2, 3 and 4, and 5 and 6. Well, what's really going on here is I've got 10 projectors, and I've got to have 10 subclasses to go with it. That's the way you get an orthocomplete eigensolution for a small part of this problem. Okay? That we'll talk about a little bit at the end here, but mostly that will be reserved for when we do the whole projectors, both diagonal and non-diagonal. But these are just the diagonal ones. Okay? So we've got 0, 4, 2, 4, not too different. And you can tell this is old because it's got color. Math type won't work in color anymore. Okay, so this is from group 3 lecture. Okay, and once again I get 6 terms, and I get the same sort of splitting of the classes with slightly different numbers. And that takes care of E. We're done with E. We've still got ways to go though, because we got to get 0, 4, 1, 4, and minus 1, 4, but don't need to do that one. I just take the complex conjugate of this one. So that makes actually this job a little bit easier, provided you don't mind working with the eyes. Okay, so there is the whole set of numbers that go with this one. And this one comes out really simple. 4, 4, and then minus 4 times, everything else 0. Okay, so that's a nice, very simple projector. It just consists of 1 and row X, 180 degrees around the X-axis, and the rest of the guys are out of here. So I get this class right there with a 1 and minus 1. So you look at a little bit of the subclass structure showing up there. And then finally, we go to this guy. This is a honker here. And this is the one that gets imaginary components on some. You can't see, the pixels are not broad enough to see it. That's imaginary, but this is a 1. That's imaginary, there's a 1. So you get a lot of imaginary terms here. And you get the unit part right here, and then you get row X with nothing, R1, R2, R1 inverse and R2 inverse as coefficients of projectors, that is, coefficients of coset there, a very complex coset. It is another way to display this. And this is nice, because when you realize this exists, then you can go directly to it and using certain other techniques and avoid a massive complete sum like this one. And T2 behaves very similarly. Again, we just get 1 and 1 for the first two and 0 for all the rest, instead of 1 and minus 1. And then here is the imaginary part. Again, eyes in about the same places they were, but with different signs, plus and minus signs. So that's it. That's those are our two things. The collected results that are in the, and this is something I forgot to reference. This is in the International Journal of Molecular Science paper, right? So I guess we ought to, label this one. But this is what we're going to be talking about in the next lecture more. And here is showing the 10 broken subclasses. And this is a matrix that transforms from that to the diagonal projectors, all 10 of them, and there are 10 broken classes. So this is kind of neat. I've never seen this done. It is a very powerful way to view. And eventually we'll, just by looking at this, get the results that we're going to be working a little bit more difficult road to obtain shortly here. Okay, now let's see if there's anything else. I can go through this. If you're really fast, you can do the calculation like this, and you're done, right? That's kind of what a computer would do, right? And this is programmable, right? All this stuff is very programmable. And the catch is, do you want to have your results in rational roots form? And that's the hard part of doing this stuff on a computer. Now, Mathematica does that kind of automatically. you can get Mathematica to take,
You don't use Mathematica, do you?
you use it to get rational roots for all your reducible representations, your characters, your Clopes-Gordon coefficients. We haven't discussed those yet, but we'd have to. Those are the tensor matrix elements in full living color. And all of that stuff can be done so that you get to have some free time. You don't have to do this all day long, right? But that is what we would really like to, I think, explore more of here, since the icosahedral group is going to be quite monstrous, but it's tiny compared to the symmetries of molecules that are floppy. That is, molecules that behave not just like a cube, but a Rubik's cube. And that is a horrendous group. That's a supergroup. And it's finite, but it's horrendous. Okay, so the question is, how do we get all of this stuff to work for some really monstrous symmetry groups? And somebody's got to do it. Could it be you? Probably not going to be me, but I hold that out. Anyway, this is the problem that is the simplest octahedral problem. And I'm using an octahedron. Literally, an octahedron composed of 8 masses. Sorry. Yes, 8 masses. The corners here, right? 4 here and 2 here makes 6, sorry. 6 masses. This is a 6-dimensional problem if I am restricting all of the vibrational motion to radial. And this is quite analogous. This is the spring K matrix right here, or if you want to call it acceleration matrix, because I've divided the mass into these coefficients, so that's what it really is. And then here is the tunneling Hamiltonian written in Dirac notation, and then a couple of coefficients that just by looking at this thing, I know I don't have more than 3 adjustable parameters if this thing really has cubic symmetry. I'm really restricted when I'm asking what is the tunneling from this well right here to just next door, which would be from going from state 1 here over to state 3, okay, or to state 5 up here, or to state 4 over here, or state 6 over here. They're all next door to this one by the same amount. So I put down these S for sneak. It's going to sneak tunnel next door here. It's got a certain coefficient of an exponentially decreasing coefficient is going to be responsible for those superfine structures in the octahedral rotation spectra. But the sneak factor for going from 1 to 3 is the same as for going 1 to 5, or 1 to 6, or 1 to 4, you see. So that's a different coefficient, but still small, than this one, which is presumed to be really, really small. This would be the tunneling that I get to go from here, and somehow you maybe go through this one, or maybe go through this high ground here to get over to number 2. That T for tunneling is just not going to tunnel. So most of the cases that we're going to see have these T's 0. Just assume they're 0. That's the model that we've already kind of looked at that model very quickly, but now we're going to solve it in some detail. Okay? So that's the quantum side. This is the classical side. Same algebra and mathematics, just different ways of talking about it. And this one is going to give us eigenvalues, which are frequencies squared, right? Whereas that one gives you eigenvalues that are the actual frequencies of the levels. Phase angular velocity. And here's the way to sum up the fact that we're going to have 4 things that are the same. This is going to be a case where the local symmetry is 0 mod 4. All of the different angles that this thing sees in the neighborhood here, this lump, this lump, this lump, this lump, belong to C4 symmetry. This lump is the same as this lump, is the same as this lump, and so forth, and all of the structures inside there are invariant to 90-degree rotations around the Z or 3 axis that is our starting point, number 1 state. Okay, and then all of the other states there are labeled by group operators the way we like to do it, but they're actually labeled by cosets, right? That's what's different now. These great big groups, you're usually making coset spaces in which to work. So we have all 24 operators here, right? But 4 of the operators are going to be labeling this one, another 4 labeling this one. There's 6 of these valleys, so 6 times 4 is 24. There are just enough operators to go around to make a coset space of each of those valleys.
What do you mean by coset space?
Basically, that I have gathered these kets, and they're the ones that are the subgroup, it's the C4 symmetry, but then the next thing we do is ask, then we're going to say we have a local symmetry here, but we're going to apply to all 6 base states the same sort of labeling. And it won't be enough just to say, take, like I did in that first slide, and let's get these 2 lined up here together so that we can compare things. This is where we actually show the cosets, but I could just say, R1. R1, that's a 120-degree rotation around here that would take me from there to there, so I could label it just the way we've always been doing it with that element, right? But that's not the only way to get there, right? There's a whole coset of elements that will get you there. It's the coset you get by taking R1 and multiplying it by each of these symmetry operators. First of all, R1, and then R3 times little r1, and this guy times little r1, and this one. That's the next coset next door here. And that's shown, I think, pretty clearly in that, which I'll bring up next here. I'll take that one back. There's a simple view of the thing without knowing about cosets. Here's what you have to do is label each of these states by cosets. And that's what we mean by coset space. It's a 6-dimensional space in this case, but it's really 24-dimensional because all of these things go along together. I go R1 times the Z rotations, 90 degrees, 180, and 270, which is what we had before while we were calculating all this stuff. Well, each of those, according to our coset arrangements that we've listed already, there's a typical coset right there. It's the one we called R1, R4, I1, R2. It's on the list down there in the 3rd screen. Okay? So those are the 6 cosets of the subgroup that is the local symmetry for this valley that we're trying to tunnel out of. And the question is, what kind of specter do we get when something like that happens?
Professor Harter?
Yes.
Would I be in error in calling that a quadruple cover? Because it's reminiscent of what we
You
did
might
with
get a lot of
SU2
people
and
to say,
03.
who? Right? That's the problem with it is, I'm going to say, a who?
Well, we had the
Quadruple cover.
SU2 and the 03. Which
Yeah. If you said that
Sort
you
of a similar
have 4 things that designate each of one valley, but really you need all of those guys if you have waves in here that aren't symmetric, right? And that's what we're going to have if I put some angular momentum around that axis and let that thing tunnel. That's going to be a whole different quantum problem, which we already have because we've got projectors that let us see those. But this particular projector has 0404. Okay, so all of the 4 in each of the valleys are, 3 of them are redundant. But put some phase on the guy, right?
you'll have to have.
Very quickly, you need all four in every one of the valleys.
So similarly, SU2 captures
Yeah.
the phase that O3 misses.
Misses, right. And this one is missing four phases in every one of
Might have some meat
by
on it.
making them equal, right? So it doesn't have lumps. Yeah. Beyond that. So basically, this is the same set of cosets, except I switched column 1 and 2. But we don't care about the switcheroo here since they're all the same. So this one makes a pretty easy problem. This is what I usually call the elementary induced representation. Where I take a scalar value of some subgroup, C4, of a bigger group, and build a larger representation than what I started with. This started with a one-dimensional C4 representation and grows to this giant, okay, that we're making here. The 6 things in it. Okay, that's a big jump. So that's an induction. And I want to also, while we're doing this, show you the mathematics, a little bit of it anyway. We've already seen the Frobenius reciprocity didn't mean much. We're going to start to see what it means fairly quickly here, and certainly by the next lecture. In any case, as I say, this coset space or coset basis spans the scalar induced representation. That would be a very professional way to say what it is we've got here in terms of mathematics, right? And I don't know whether quadruple covering would be used. You might be chased out of the room for that one. But
I see meat on it.
yeah, right. I mean, if you learn the terminology and it doesn't bother you anymore, then it's good. But basically, you see what we're doing here is we're looking at, for example, doing an I4 on 1, okay? Well, I4 is in the coset that has R1 squared, okay? So that's just showing that I can get the I4 turned into an element that I'm more familiar with, okay? The I4, I mean, it's kind of stuck off at an angle here and it's going to do something, but I can sure see a lot easier using, instead of I4, I use R1 squared, Rx squared, 180 degrees around the number 1 axis, the x-axis, right? In other words, I'm just going to grab that thing and, like Al did with the cube, turn it completely over. That I can see, right? Whereas I4, you know, it's down here and it's a little hard. It's actually pretty easy, so you got to go around that way. It's very different from going around that way. If it weren't a 0-4 cluster, right, or cosets basis. So anyway, R1 squared 1 is number 2, okay? R1 squared, this guy right here is a leader of the cosets. We're using these guys as leaders in that particular one. R1, R2, little r1 squared, little r2 squared, the way these things are labeled, okay? That's just because I didn't want to take all those guys along for the ride if I didn't have to. So that gives you this relationship. So I4 times I3, now I can get used to just using I4 on number 3, and you got to find number 3. Where is number 3? Ah, there's number 3 right there, and you can see where, that's a little bit hard to see, but you can see he bisects the line between this and this. So it looks like the I4 rotation would take 3 into 6. Okay, and so I eyeballed it. I didn't have to go through the group multiplication to get that, but just by looking at this thing, I can see that this axis right here is halfway between this axis and this axis. And it's that kind of visualization skill you may or may not have developed, but if you have, you don't have to go through a group product to get that. And similarly, I4, that's this axis again, working on number 4 state and so forth, turns it into number 5. There's number 4 way over there, and that's going to bring me up to here. You see, this thing is bisecting that set, so it's going to drive that axis into the X, and that's this one. Again, I didn't need to go to the group table to get that one. And similarly, okay, so I picked a difficult operator here, I4, it's sort of cockeyed, but it doesn't matter. You can still see, just if you like you do on that cube, where these things all go. So then it's just a matter of collecting these Bra equations into a matrix. And that's how you make an induced representation. This is the simplest example of making an induced representation. We've taken this one-dimensional representation of C4 and we've jacked it up to this enormous symmetry octahedron. Now, it's not an irreducible representation. We know that. We know from the correlation table there's a A1, an E, and a T1 in this thing. But thank God for small favors. This is an easy way to see what an induced representation is. Probably the easiest non-trivial example I can think of. Okay? So I'm going to sometimes write it this way. Script I from Edmonton, what is it? What is the name of this fancy script that you use on wedding invitations?
Edward.
It's Edwards or something like that. So there's the induced representation, that's an I
Okay, that's a script
on a
that I
wedding
know.
invitation, right? And then 0 mod 4 up to octahedron of the element I3 in the octahedral group. And it's got, you already know what it's got in there hiding is A1, E, and T1.
So once again, what does the arrow, the upward arrow mean, the part?
It means the opposite to the one that you have better feeling for. And that's where you go the other way. You take like T1 of the octahedron, right, and arrow down to C4, right? And that splits you up into, you probably already know, 1 mod 4, minus 1 mod 4, and 0 mod 4, right? So you make a correlation table between 0, 1, 2, and 3 mod 4 on the top, and then the group O, A1, A2, E, T1, T2 on the side, right? You see the arrow down by reading across this way, right? And by looking down the columns, you see the arrow up. The induced representations that come from taking that little guys at the top and blowing them up. Better way to state it for a physicist is you put your 0 mod 4 in one of the wells of this system and stand back, right? And what does it do? Sneak, 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 and pretty soon it's all jumping in every one of the wells, right? It's using induced representation bases to do that, if you're thinking it mathematically. The spectra is being made out of exactly this space, this coset space. This is just showing a couple of other ways, and this is a nice way to go ahead and write the Hamiltonian. I won't dwell on this one right now. We'll have more of that later on. But I want to reduce this representation as though I didn't know what the story was, and the idea is I'm going to take the kets from the projectors, and this one's really simple. This is a sum over all of the group elements with a factor of 1. Well, actually, 1 over the square root of 6 if you want to normalize it, okay? If it's a classical problem, this is just what's called the breathing mode, where all of the atoms go together out and together in, and that's just showing their initial velocity, I guess, but they could also be showing a position they're going to get in a quarter period, okay? So this is very classical, understandable. This is the A1 part of that correlation table that goes with this particular 0-4 induced representation. And then here's the same thing written as a eigenstate of a Hamiltonian, and here we're imagining the wave functions with little tiny splittings between the ones that are tunneling. So here we have 6 different wells arranged in an octahedron with narrow necks between them. And the analogy that I made in the last lecture was between this and that thing that's on the screen down there at the end of the room, where I have 6 waves oscillating in some way. That particular one right there is a scalar, not a scalar, that's a vector wave. Let's get the scalar one going so it looks very much like the thing that we have here. I'm going to kill this one, which is an E wave, and start up the ground state, the lowest state. And there it is. All together now. High, high. This is Trump getting out the helicopter. High, high. Okay? Very simple. Very simple. And that's what this is. You got to think of this thing oscillating inside there, right? Don't have to think about it oscillating here. That's the whole story over here. Very different physics. Mathematics identical. Okay? Here's the top of the line right here. This is the E00, whereas this is the A100. So we've got a projector for that one. I'm not going to go back and look at the coefficients of all the cosets, but this is what you get. Okay? Basically you get 2 1s and then a bunch of minus a halves. So you get 2 big lumps that are in plus phase, that is plus on the phasor scale, and then these guys are out of phase with that, all 4 of them on the equator of our so-called north and south pole, just laying over on its side right now. Well, this is the mechanical thing. This is called dilationless strain, I think, dilationless stretch, actually. What you do is you pull on this guy by 2, and these go in by 1/2, and you end up not changing the volume. And that's what dilationless means. Okay, so it's a famous tensor, right? Well, that's what this is. This is a famous tensor of the quantum kind that we've been working with. Okay, so we've got the lowest state, and then we've got 2 states up here. Where's the other one? That's the thing we can't get today because we only work with diagonal projectors. But if you do get, and that's what we'll do in the next lecture, go and get the 2 mod 404 projector. That is something that has global symmetry 2-4, but local 4. It's still local 0-4 there. You'll see the other side of this cell, the orthogonal combination of waves. Okay. Well, you've seen this. This is 2z squared minus x squared minus y squared. Right? And this is x squared minus y squared, with a factor of square root of 3 to make it so it has the same normalization. Okay? So, again, that's the way, that was our top-down tensor, right, that we got the T2 representation out of, and the E, which is what we're seeing right now. One thing left out of this is this guy, T1. And we only have, again, 1 state of that. The global symmetry will go through 2 different choices besides this one. This one, that was the only thing we had. But we've got to handle that in the next lecture. Going and just working with a whole irreducible representation so that we get global and local. Right now we're just getting examples of the local. Well, this one is pretty easy. This is just those 2 masses going back and forth on one axis, everybody else not moving at all. And here we have a situation where we have a wave function plus and minus. It's a vector in the sense that they're out of phase, but there's nothing on the other vertices. It's 1 minus 1 vector, all the other 4 zeros doing nothing. And this is what we're going to be seeing when we go to the plus and minus 1, 4, 0. Here's the global symmetry, plus and minus, still only a local 0, 4. That's a moving wave. It's pi over 2 out of phase, and then pi out of phase, and then 3 pi over 2 out of phase, and then back to 0 again at the top. So it's capable of pinwheeling. If you take combinations of them, make standing waves out of them, that's what we would have gotten if we picked instead of C4, we'd pick D4 and D2 as our subgroup labelers. We would have come to this and had no complex numbers anywhere. Well, that's just translation in 3 different directions. This is dipoles pointing in 3 different directions. Again, same mathematics, very different physics. And the other thing that we're getting from this is when we stick these vectors into the matrix right here, with the tunneling across town, as I said, extremely small, so small we'd set it to 0, and then the other 4 small but all equal, then we predict that we will go down twice as far as we go up with the EG, twice as far to the ground state from the vector mode as we go up for the EG mode. And not only that, if you look at those waves, you see this is very even, very even, plus plus, minus minus, minus minus, minus minus, plus plus. They're all balanced, okay? This one's down here, same thing, plus plus on all 6, right? This one's plus minus. This one inverts, gives a minus sign. This has negative parity. These have plus parity, G parity, G parity. Ungara, uneven, odd. And that's something we got from that correlation table using OH, right? So, as I say, we're taking this as a stages. There's so much that we can do with things that are invariant. That's why, as I say, many people in these fields just does the character stuff, the invariant stuff. That's what we were talking about. Labels correct U or G parity, okay, in this correlation here. So I don't just get A1EG and T1G. I get the T1U way down here. Remember that? That's it. You can see very clearly from that picture there that that's what it is. And this is an actual spectrum, a low angular momentum spectrum by Alan Pine. Quite a while ago. First see, and it's the first time somebody realized that they're getting clusters in methane. Methane, you can't heat it. You know, it doesn't go up to high J when you heat it. It's so light. It's just hydrogens rotating. It's not big nuclei rotating. It's just hydrogen. So your room temperature distribution is lucky to be able to see anything out here, and this is angular momentum 10. And there's a cluster at 2-to-1 splitting. So that was first, I'd say the first example where we're seeing this for molecules that people really know a lot about. Methane being almost as common as a global warming gas. Anyway, I think this is a good time, probably, to start, but this is what we're going to talk about next time. This is what I've already shown, is you can just use this table with diagonal projectors and just look what happens when you have I1, 2, 5, 6. That's 4 different parameters that are all equal. That's the global O4 symmetry demands that. Okay, if that's the case, then you've got a +1 here, and a -0.5 here, and 0 here. So there's your T1 right there, sitting in the middle, and this one is +1 up here. Doesn't get the fact that the tunneling is a negative sign, so this would be turned over, but it gets the 2-to-1 splitting. 2 to 1 from T1 to the A1 is twice as big as the splitting from T1 to E. And because of that rational splitting, the dynamics of mixing these states would be periodic, absolutely periodic. Here's the other side. If you let the tunneling be just crosstown, that's I3 and I4, remember those two axes that this had? There's I4, there's I3, okay, right there and there. They're really special in the sense that they're perpendicular to the main axis of your, what you call your origin for the symmetry analysis of this, okay? So I3 and I4 make a subclass, and so does I2, 5, and 6. They're all the same, but they're made by those rotations I1 through to I1 and I2 and I5 and I6. I3 and I4 are the ones that take you crosstown. So this is next nearest neighbor tunneling effect. And you can see that it makes the A1 and the E next to each other, on top of each other, and the T1 goes the other way on that one. So if you have a mixture of those two parameters, then you don't make anything. So you have just enough parameters for this in this problem to make all of the possible states subject to the local symmetry.
So it's like you have three independent two-well problems there,
You could look at it that way.
because there's no
Absolutely.
talk
Yeah.
between the pairs.
Yeah. Okay, I think they're showing all of the axes, so you get a feeling for what these things do. So I think I'm going to just stop with this, but let's just remember where you see this cluster, A1, T1, E comes in when your Z component is divisible by 4. This is a K equals 30 thing, so there's a 30 up here, which is the 0 mod 2, I'm sorry, 2 mod 4 cluster. This is 1 or 3 mod 4, actually 1 mod 4 exactly, is 29, okay, and then 28, all right. And then you'll see this again when, and you got to go through the 2 mod 4, but you'll see hiding in the forest here an A1, T1E, and even in the disastrous region of the Separatrix where they're all shooting at each other, we still maintain a 2-to-1 splitting, roughly, roughly. But it's really close to 2-to-1 here, to many figures. This is splitting here at 10 to the minus 8 inverse centimeters. That's cycles per month, right? Well, not quite that slow, but it's really slow. Okay? 1/10,000,000th of an inverse centimeter. An inverse centimeter is in low infrared. That's a Kaiser. That's 1 Kaiser. This is a 1/10 of a micro Kaiser we're talking about here. For this Kaiser. And then this is even less than that. 10 to the minus 10th is at the top there. Okay, let's, any questions, any comments?
How you are able, you show us at the very beginning a picture of the spectra of a molecule.
The spectra being
Like the
a whole panoply,
Yeah.
starting with the, say, infrared band total
Yeah.
of resonance, and then dropping into the,
I think you have it
this guy.
somewhere.
On the wall there
Yeah.
are the
that.
panoplies.
Uh-huh.
SS6 at the very top left.
How were you able to measure that? Like that's
Let me go around and sort of point at that figure, because we did actually look at that figure a couple of times already, and I'm talking about
yeah, but I
this
still
one right here. This is simpler. This is Freon. This is a tetrahedral molecule. The tetrahedron's half of a cube.